So, welcome to today's lecture. So, in the last class we mentioned that what are the modified Nusselt number and Sherwood number in this particular case. So, now let us look at the what is the form of this f, which we already mentioned in the previous lectures. Here we will once again, for the sake of completeness, we will reiterate that. Okay. So, Scirinniano, this is Abramson and Scirinniano's model essentially. So, they, as I said, that et al. Used the Faulkner-Scan type of solution, which, let me reiterate, is flow over a wedge, basically flow past a vaporizing wedge, flow past a vaporizing wedge. Okay. So, it is a laminar boundary layer that is actually formed. So, in those cases your there are some restrictions on the BT and BM. Okay, so they are both less than 20, and this we already mentioned earlier, the Schmidt number and the Prandtl number were less than 3, and the beta, which is basically the wedge angle, is within this, right. That was what Scirinniano used, flow past a vaporizing wedge and the corresponding laminar boundary layer, right. So, using similarity solution, what he showed, this we also narrated earlier, that FB was nothing but 1 plus B raised to the power of 0.7 ln 1 plus B divided by B. This we did in the last lectures, right. So, using the solution, using similarity solution here, this is what he showed, right. So, there are some interesting exercises that people did. People studied what is a variation of this FB. This FB has got some variation, right. So, people wanted to study that what is the variation of this FB in the current context. So, they found that FB varies from basically 1 to 1.285, okay, as B, which is basically the Spalding heat or mass transfer number, varies from 0 to 8, okay. And when the heat transfer number was within 20, 8 to 20, this FB is basically a constant, it does not vary at all. This was an interesting observation, right. So, there was about a 30% change in FB when B actually increased from 0 to 8, right. But there is a corresponding saturation of FB also, that means a near constant value of FB for the major part of B, that is from B from 8 to 20, it does not change at all. Okay. So, that was a good thing that was devised, that was observed. Okay. So, using that, when you actually, what is your m dot? M dot, we are going to substitute all these things into m dot, because SH star and all those things were there in m dot. Let us look at the mass transport limited m dot. Okay. So, this is RS 2 plus S naught minus 2 divided by 1 plus. So, I am substituting everything over here, 0.7 ln 1 plus Bm divided by Bm, close it, 1 plus Bm. If you look at this now, this and this gets cancelled. Okay. So, your m dot basically scales as some B, this B goes into the top, right, some B divided by 1 plus B, let us keep it generic. So, because this will be valid for the other one also, right. These two gets cancelled. Okay, this Bm goes up. So, this is basically B by 1 plus B to the power of 0.7, right. So, this is valid for a very large set of Reynolds number, actually 2000, and for B less than 2.8. Got it? Clear? So, this comes from basically substituting the value of m dot. So, we have just substituted for what? We have substituted for SH star and FM. These two have been substituted here, right. That is how we got this expression. Now, also note because we still have these two numbers which are basically unknown, right, SH naught and NU naught, this is the Nusselt number and the Sherwood number. So, note that those are given by standard correlations. This is for non-vaporizing sphere, okay. And it actually has been shown that it overestimates it overestimates for Reynolds number less than equal to 10, okay, because this is for non-vaporizing, because these are for non-vaporizing, right, as we already stated, okay. So, Clift et al., they actually suggested a modification to this. All these are very empirical sometimes, okay. So, do not be bothered about the nature of the thing, that is because as you know in fluid dynamics most of the problems do not have a clear cut solution. So, you have to resort to this approximate analysis. So, these are not exact analysis, these are all approximate analysis, so to say, okay. So, 1 plus Reynolds number Schmidt number to the power of 1/3 F Reynolds number, right. So, this is valid for Reynolds number less than equal to 400, up to that limit it is actually valid, okay. Now, this FRE has got two forms. FRE is basically equal to Reynolds number raised to the power of 0.077 and FRE is equal to 1 for Reynolds number less than equal to 1. This is for Reynolds number greater than 1, right, okay. Let me put a demarcation mark here so that there is no confusion, right. So, these are that factor. All these are very empirical, but I want you to get a feel of the thing that the mass evaporation rate is a function of the heat and mass transfer numbers, right, okay, and the normal non-vaporizing Sherwood number and the Nusselt number is given by that particular expression, right. Now, we once again revisit the liquid phase analysis. Now that we have done this, the liquid phase analysis becomes whatever we did earlier, right. Let us put all these things in perspective now. Now, the liquid phase analysis, okay, what we have to do, as I said earlier, that we are interested to know what is the temperature distribution, right, and how it looks like with evaporation of the droplet. So, you already know that QL is basically given by this, right, and this is correct, that is what it is, right. CPF, this is the enthalpy, this is the specific sensible enthalpy part, that is the latent heat part, right. So, this goes towards the inside the droplet. So, what we to predict the temperature inside the droplet. So, our job is to basically predict the temperature distribution, that is one of the important thing, temperature distribution, right. To do that, what people normally do is that we assume that there is an infinite conductivity model, right, that is what we did. Infinite conductivity model means the KL of the liquid phase, KL or lambda L, whatever you call it, is very very high, right. So, that means the temperature is spatially uniform, but temporally varying. Temperature of the liquid is spatially uniform but varies temporally. That was the infinite conductivity model, right, infinite conductivity model. We have already seen this, right. Right. Similarly, there could be a conduction limited model, conduction limit, okay, where heat transferred through the droplet solely happens due to thermal conduction. Okay, so the conduction limit is that heat transfer inside the liquid phase happens only due to conduction, right, solely due to conduction. And of course, the surface temperature is uniform, correct. Is that clear? So, these were the two models that we already looked at earlier, right, the conductivity limited model and this, right. However, now we have a situation, as we said earlier, there is intensive internal recirculation, and what is the role for that? We are interested in this particular portion, right. This is caused, as we said earlier, by surface friction, nothing else other than surface friction. Okay. And we already have defined the Reynolds number as US into d of the droplet rho L by mu L, and the Peckley number is given as rel. So, this is basically, as we said, is a U max or maximum velocity at droplet surface, right. This is, we already said that it is greater than equal to the Reynolds number, the normal gas phase Reynolds number, right. So, here we already said something about the vortex model and how it does a very good job, in which the flow inside the droplet is represented by the Hill spherical vortex scenario, right. So, here we said that Hill spherical vortex, and we already said what are the equations that it solves. Hill spherical vortex is actually a reasonable solution. Okay. And of course, we continued that the surface temperature is uniform. We said uniform, we did not say it is constant, right. We did not say that the surface temperature, there is no spatial variation, it is only at the surface that the temperature is uniform. That means along the surface there is no temperature gradient, okay, which would have brought the Marangoni and other kind of stresses into the picture. And in reality that can happen actually, because you have a wake behind the droplet, okay, and all those things. But for the time being, for in this particular consideration for the vortex model, we are assuming, and for many other models also, we are assuming that this surface temperature is actually uniform across all levels, okay. And this Peckley number is also high, it is actually sometimes greater than 10, greater than 100, in most of the times it is actually greater than 10 at least, okay. So, high Peckley number situation, okay. Now, let us look at from the Hill spherical vortex what we have. If you cast it in terms of velocity, this is a radial component of the velocity, okay, and this is the corresponding tangential component of the velocity. Okay. So, these are velocities given in the spherical coordinates. If you are unsure about the spherical coordinates, I suggest that you pick up a fluid mechanics book and see, okay, that how it happens in the spherical coordinate. So, this is basically the radial component of the velocity, this is basically the tangential component of the velocity. So, these are the two components, okay. We also assume that the Hill spherical, these velocities are by the way variable, okay, they are not constant, okay, but we assume that the Hill spherical vortex applies to the unsteady situation also and during the vaporization of the droplet. The simple reason is that we already established that the vorticity transport happens in a much shorter time, okay, and that is the reason why this we can actually go by it, okay. So, even when the, so formally writing it, Hill's spherical vortex solution is applicable for number 1 vaporizing droplet, right, okay, vaporizing droplet, and unsteady. And we already established why that should be the case. Okay. And we also see that the streamlines are insensitive. This is an important observation, insensitive to internal Reynolds number, that is REL. So, the streamlines are basically insensitive. There is an experimental confirmation also on this. So, people who have measured the velocity inside the droplet, you can see that the streamlines are basically insensitive to the liquid phase Reynolds number. Okay. Now, to look at some of this thing, okay, and in order to explain one final time, so we already established, let us go to the next page to have the screen. So, the hydrodynamic characteristic time of establishment of velocity. So, this is the time for establishment of velocity within the, or stabilization of velocity, velocity stabilization within the droplet, Now, that is given by when the Reynolds number of the liquid phase is very, very low, much less than 1, basically viscous, the entire droplet is basically viscous. Okay. Let's take a droplet of honey, okay, or a glycerol droplet, which viscosity is very high, okay, and that will give rise that the velocity inside the droplet will be very low. So, in that particular case, your T hydrodynamic is basically scales as Rs square divided by gamma L, right, which is the kinematic viscosity. Now, in the high Reynolds number, that means the Reynolds number much greater than 1, high Re, this same T hydrodynamic therefore now will scale as Rs by Us. Us is nothing but the surface velocity, right. So, in other words, this will be equal to Rs square divided by gamma L into Reynolds number L, all right. So, what we can see is that if the Prandtl number now, so in this particular case, okay, one can readily see that this hydrodynamic time scale is much shorter than that, no doubt, right. This hydrodynamic time scale should be much shorter than that. Okay. Similarly, if you talk about some kind of a thermal scale, okay, thermal scale which is responsible for some kind of a, say, the temperature differential, okay, that will still scale as Rs square by, say, alpha L, right. And in the usual case, this T hydrodynamic is actually much shorter than this T thermal. Okay. So, this basically justifies that why the Hill spherical vortex is always a good solution, okay, and why it is actually a quasi steady kind of a thing. Okay. And this happens also because your Prandtl number is always of the order of 1, of the order of 10 over here. Okay. Now, the key feature that evolves out of this, if you look at the previous slide, so you can see that there is, in order to compute these two velocities, we need this Us, which is the surface velocity, right. We need that. So, how to actually calculate that is the question, that is a long standing question. So, it should definitely come from the friction, because that velocity is induced by friction, right. So, let us calculate the friction force. So, when we calculate the friction force, this is Rs square is the r theta g sin square theta d theta. So, this is the shear stress on droplet from gas side, coming from the gas side, right. That is why you wrote the G over there. And we already said that this r theta g is the same as r theta L, right. Why that happens? Because there is no surface tension gradient. We already said that, right, uniform temperature across the surface, right. So, what we do immediately after this is that now that we know, evaluate r theta L from Vr and V theta, that is easy, right, because you know what T r theta is, right. So, it is basically the cross derivatives. So, once we know that from here, and I am not showing the steps, again the steps are messy. So, this is US is 1 by 32 delta u infinity, which is basically nothing but the relative velocity, mu g by mu L R e into C f. Now, this is basically a relative velocity, okay, between the gas phase and the liquid phase. This is basically a skin friction coefficient, comes from the friction, right. So, this is like a skin friction coefficient that we have. Now, this skin friction coefficient in turn is a function of the Reynolds number, mu L, mu g, of course, rho L, rho g, and it also depends on the Spalding heat and mass transfer numbers. This is like simple common sense, intuitive sense should actually tell you that if this is the velocity profile that we get at the surface, then it must be dependent on these parameters, okay. Now, for a solid non-vaporizing, again we move to the same type of analysis for a solid non-vaporizing sphere, what we have, Cf is basically given as 12.69 Reynolds number to the power of minus 2/3. This is valid between Reynolds number all the way up to 100, 10 to 100, right. So, for example, if your Reynolds number is 100, okay, and mu L by mu g is greater than say 10 or 55, okay, this US by delta u infinity, that is the relative velocity, will be given as 0.184 and 0.0335 respectively. This is just to give you an example. You understood. So, when the Reynolds number, external Reynolds number is of the order of 100, is mu L by mu g is of the order of 10 or 55. You can see when it is 10, that means the ratio of the density of the viscosity between the liquid and the gas is only 10 times, okay. The gas is obviously 10 times less viscous than the liquid. You have that your US, that is the velocity that is created at the surface of the droplet inside the liquid phase, right, is actually about 20% of the velocity of the relative velocity, right. So, if the relative velocity is say 5 meter per second, this will be more like 20% of 5 meter per second, got it, okay. On the other hand, as we increase the viscosity ratio to 55, that means the liquid phase perhaps has become a more viscous fluid, say for example, it has become glycerol, a glycerol water mixture, something like that, right, okay. You will find that the velocity of US for the same velocity in the external phase is actually a much lower number, it is only about 3.5 times, 3.5%, right. So, you can see as you make the inside of the droplet more viscous, less will be the velocity that will be created by this surface friction, right. If the viscosity difference is very small, okay, like of the order of 10, right, significant amount of velocity is actually created inside the liquid droplet. This is quite obvious, that is because it is the viscosity which actually determines what kind of a velocity you will generate inside the liquid phase for a given outer phase flow field, right. So, we have kept the outer phase flow field, that is the Reynolds number, to be the same, that is 100 in both the cases, except we have played with the viscosity. As you make the viscosity ratio higher and higher, you get lower and lower surface velocities in the liquid phase. So, that is an interesting observation that we have over here, okay. Okay. So, moving on to the next one, Okay. So, for evaporating sphere, so this is non-evaporating, for evaporating sphere, okay, friction is reduced by surface blowing. The friction is reduced. So, your Cf will be 12.69 into Reynolds number to the power of minus 2/3, sorry, with the wrong expression. So, when you actually have the Reynolds number, you have the skin friction coefficient, this 12.69 still remains, this Reynolds number 2/3 also remains, you have 1 plus Bm that comes over here. This is valid for B less than 0.78, whereas the same expression will be 12.69 divided by Reynolds number to the power of 2/3, 1 plus B raised to the power of 0.75 at B less than 20. Got it? Okay. You got it? So, this particular part is quite obvious. Now, the skin friction coefficient is given, is actually reduced because of the surface blowing, because of the thickening, okay, of the boundary layer, right. So, this will in turn reduce your US, that means the surface velocity that you are going to generate inside the liquid phase. Now, we are in a perfect, now that we have analyzed everything, you know US and everything, now the transient heat transfer now is, transient heat transfer now can be solved. How it can be solved? And this is a long equation. Is all non-dimensionalized. So, you can open it up and you can see it yourself also. This beta is not the same as the wedge. We will show you what that is. Sin theta, complete spherical coordinates, got it? Long equation, nothing to be afraid of, it is a spherical coordinate. We have written basically the advective, convective advective equation, okay, within the liquid phase. So, your Rs prime is basically equal to Rs by R naught, R naught being the initial diameter, neta is the normalized R axis, Vr prime is basically Vr by Us, V theta prime is basically V theta by Us, Z is basically T minus T naught by T naught, tau is basically alpha Lt by R naught square, okay, and beta is basically equal to, not the wedge angle. I know that there are some notational issues always, d tau, okay. So, this is basically proportional to the surface regression. Got it? Okay. So, this is the complete equation written in a non-dimensional fashion for you. Okay. So, this is subjected to some initial and boundary conditions. A tau equal to 0, Z equal to 0, this is the uniform initial temperature, right, that is the initial temperature. B at neta equal to 1, that means at the surface of the droplet dz by d theta is equal to 0. Okay. This is once again uniform surface temperature at any point. This we said, right, the surface temperature is always uniform regardless, right. Okay. So, there is no theta variation. Theta variation means there is no angular variation. If you take this as your droplet, so this is your theta. So, in this theta there is no variation, right, which is makes sense, correct. Okay. And dz by d neta sin theta d theta is equal to ql divided by 2 pi rs kl t naught. Got it? Okay. So, this is nothing but the total heat flux. This has been integrated across the entire surface, and this is the symmetry line. So, we have done it only up to pi, right, because this is half the droplet, this is a full droplet, this is symmetrical. So, from here to here is basically your pi, right. So, you have integrated. So, this means that it has been integrated across this entire surface, right, to give you the total heat flux, right. That should be quite obvious. Okay. Then there is the symmetry condition. Right. Symmetry condition is at theta equal to 0 and pi, d theta by dz is equal to 0, right. Okay. Got it. So, now that we have done all these things, now you should recall that when Peckley number approaches 0, that means the flow velocity within the droplet actually goes to 0. This reduces to a conduction problem, approaches a conduction problem. Okay. And so, the equation basically gets changed. So, if you write the same equation, right. Okay. Okay, because I have just taken off the Peckley number term. Okay. So, at high Peckley number, this is for low Peckley number, for high Peckley number, okay, the convective transport inside droplet, the droplet, okay, is stronger than thermal diffusion. Obviously that is the case, right. And so, the isotherms basically coincide with streamlines. Okay. And of course, there is the other limit KL, or you can write it as lambda L. As that approaches infinity, this is called basically the infinite conductivity model. Got it? Okay. So, this particular equation, there is no way that you can solve it. So, you have to solve this numerically. So, in the next lecture, what we are going to do is that we are going to see that what are the numerical outcomes of these processes. Okay. So, numerically these are solved, cannot be solved in any other way, right, but we have shown that from the main governing equation what you can expect. You can expect that your streamlines and your isotherms should kind of match each other. Okay. That is the case when you have a high Peckley number. For a low Peckley number, this would be more like a diffusion based kind of a problem, right. So, these two things, if you can analyze it, and within a droplet lifetime also this can actually change, because Peckley number is not constant across the droplet lifetime, because your Reynolds number is varying outside. So, your Reynolds number inside the droplet will also vary, right. As a result of that, your Peckley number is also going to vary, right. So, all these things dynamics combined, we need to see some results basically to understand what are the physical interpretations. So, these are basically solved in a numerical fashion. So, numerically these problems are basically solved, because there is no other way of solving it, and we will look at some of the numerical results in the next class. We are also going to look at some alternative approaches. Some alternative approaches are also there. Okay. So, those alternative approaches we will see in the next class. Okay. Thank you.